think we could slowly start. So, good afternoon, everyone. Welcome to the final lecture of this mini school on application of machine learning to the high energy physics problems. And we're looking forward towards the second lecture of Palab, in which he's he's planning to tell us more a little bit of practical implementations of machine learning to the relevant problems. Thank you very much. Palab, you can start.
Hi. So previously we was talking. Can you see my screen?
Yes.
Okay. Now let me just check. So can you see some other things like
Yes.
Zoom?
Yeah. Yeah.
You
Yeah.
can.
I can see your Firefox. Yes, I can see
Yeah.
now
Okay.
Zoom.
Great. That. So if I show the Firefox, you guys can see. That's what I want to just
Yeah.
make sure. Okay.
Hmm.
Okay. So I'm starting then. Okay, so basically we're talking about restricted Boltzmann machines or RBMs. So I'll just show you today a little bit on how to program RBM a little. So what was RBM? RBM was, and why that was interesting is RBM is easy to code. So maybe we just use RBM today to code, means see that what is going on. So we'd have a good idea that how things are done. So RBM is an example of a generative model. And we are restricting ourselves to one output layer and several hidden layers. But today we'll just restrict ourselves to one hidden layer. So what does a generative model means? So generative model means that as I have shown you about Ising model, etc. So there is a spin system. And in the spin system, the spins can have two phases like blue or red, etc. That is up and down. So the whole thing you may think as a stochastic input, a stochastic chain of vector means spinner 1, 0, 0, 1, etc. So for example, this kind of lattice configuration is a vector, means that in each side you have a number 0 or 1 depending on the spin is up or down. Okay. Now, so suppose this visible layer in RBM contains that input information, or you can generate some random number by coin toss, say head or tail, which is called Bernoulli, means distribution. That is distribution of head and tail in a coin toss. And then you ask the RBM, you show the data to RBM. I'll tell you what is meant by showing the data to RBM, and then ask the RBM to reconstruct this data. What does reconstruction means? Reconstruction means that suppose I give some input to the visible layer, somehow by some mechanism, whatever it is, we turn on all the hidden layers. Okay, and turn on some of the hidden layers. I'll tell you what is the mechanism of turning on or turning down, and then we in reverse step. We what we do is that we again turn on visible layers. Good. Now you start with the visible layer, some configuration, and then you turn on certain hidden layers, and from them you again turn on. And I'll tell in each step what is the mechanism of that. You turn on again the visible layers. Now you demand, what you demand is that this new visible layer, which you have got from the old visible layer through this process, is called reconstruction. So you may see that some picture like that is given here. Sorry. So this is layer one. So some visible layer comes, then there is a it turns, it does something to the hidden layer, and then you again reconstruct the visible layer. So from one visible layer, you are going to a reconstruction of the same visible layer. Once you do that, so the idea is that this is called reconstruction. Now, it could be shown that RBM could be trained using this reconstruction. What is the goal of a generative model or RBM is to capture the distribution of the input. Means that you show it enough number of input, it learns the distribution, then it can reproduce the distribution at its whim. Reproduce means you can then what it can do is as a Monte Carlo chain, it can choose various values of hidden layer just randomly and generate the corresponding visible layer, and that itself will give you a good distribution of the distribution of the visible layer that you just give input as a data. So goal of a generative model is to generate certain distribution, as I have shown that in the case of Ising model, etc. There is of course a thermal probability distribution of various configurations, and in RBM in those cases would try to generate those configuration. And even if it is not a spin model, if it is a quantum field theory or something more complicated, RBM will try to generate those configuration and the probabilities of getting one configuration. Remember that quantum mechanics, when you do the Euclidean version of quantum field theory, it's just a probability thermal means some probability is assigned to a lattice configuration. Given a configuration, the e to the power minus the action gives the probability of that configuration. So if you can generate that probability, you can in principle do and look at various things of quantum field theory from the viewpoint of RBM. Now, why is that useful? We'll see why is that useful if we can. But the first is that this kind of learning system, what it is doing is something very interesting. Look that the number of hidden layers, as you can clearly see, is generally less than the number of visible layers. So when you are going through this reconstruction process, which I have shown that here, like from one to another layer. So what is also happening is that the system is going through, ignore this plus one for now. So system is going through some kind of bottleneck. So when the system goes through bottleneck, the system loses some amount of information. However, if the reconstruction is good, that means the system has actually kept the most important part of the information. So this through by putting the system through this bottleneck, what you do is that you learn a lower dimensional representation for for the variables which are necessary to generate the probability distribution of the input. So these lower dimensional variables often contain important information about the input. Okay. Okay. Now, how is it done in practice? So RBM is given by this kind of a action given by AIVI plus BJHJ plus VIWIJHJ. Means that it is some kind. AIVI, what does it mean? It is kind of chemical potential for VI, and then there are chemical potential for B's, and then there is an interaction term VI omega IJHJ is the interaction between V and H. And then what it does basically, the RBM will be producing. So what we do in the first step is that given an input, we kind of generate the hidden layer. And we generate by this formula. This sigma is the activation function. Activation function means something very much like a tan hyperbolic function, means basically it is 0 on one side but and 1 on another side. Little different than tan hyperbolic, but it is basically again the sum of two exponential and divide by sum of two exponential. So basically it is e to the power x, I think, by e to the power x plus e to the power minus x. So it is changed from 0 to 1. So this function is generating, means designed in such a way. So this is activation function. If you search for, you'll see what this function really is. So this sigma x is sigmoid function 1 by 1 plus e to the power minus x, or e to the power x by e to the power x plus 1. This function is called the sigmoid function, and this is often used as the activation in neural nets. So we are just using this function. So what is it doing is that, so it is activating the necessary, so given a visible input, there are weights of the RPM. Weights sits in, so this weight sits in these links. So each link has a weight associated with it. And what we are doing, according to this weight, we are activating or deactivating the particular layer. Means that we are taking a probability that given a V, so this is a sigma, means we just choose our V's, and then through these formulas we generate the hidden layer. So that's how we generate from visible, we go to the hidden. And exactly given that hidden, again through these sigma functions, this is the probability we can sample through this function and generate our visible layer. So from the visible, through the sigmoid function, we go to the hidden layer, and from the hidden, we come back to the visible layer. Okay? And once we do that, we have solved, we have done one reconstruction step. And the claim is that the reconstruction should be good. Now, what is meant by the reconstruction is good is a very difficult question. So this question is only partially solved, but according most people, what they do, as has been discussed by this famous paper by Hinton, who is a senior professor in University of Toronto and a famous computer scientist, and who was one of the creator of restricted Boltzmann machines. So in his words, so the one practice generally people follow, but this is not the ultimate practice in a way that you can do various things, is that basically you look at VIHJ, this product for the data, and VIHJ, this product for the reconstruction. And now this VIHJ, these quantities for the data and this VIHJ for the reconstruction, you need to see that some of these quantities are one go quantity. These are not, there is no probability sampling here. So which makes this calculation much more easier. What you do is that you get, so you have a set of data points, which is VIs, and then you multiply that with a, you reconstruct for the first step, you generate the hidden layers, and from the hidden layers you calculate these quantities VIHJ and sum it over and take the expectation, basically the sum over this quantity over the data, and that will give you this VIHJ for the data, and you just do the same thing for the reconstruction. So this quantity, if you calculate the difference between them multiplied by some learning rate, will tell you how the weights needs to be updated here. Okay, so you can see that if the reconstruction is 100% good, if reconstruction actually produces whatever value of VIHJ, this product you had for the data, then this thing will be zero. The weights won't be updated anymore. That means that weights will become static. That means you have come to an optimal point of this learning landscape. So if reconstruction is good, then this weight update will slow down. Basically, what this equation 9 does is that actually it is stochastically drag you near the point where reconstruction is relatively good. If the reconstruction is not good, this weight gets updated and you travel in this landscape, and once they become better and better, you kind of stop near that point. So this way, this is called a typical gradient descent kind of method, although it has been shown that this particular function is not an exact gradient of any function. And that's where the confusion lies. I say that in what way it is good is not still clearly answered, knowing that we don't know whose gradient this function is. We can prove even that it is not gradient of any function, but it may closely approximate gradient of some function, and there was some proposal that which function it could be. But there may be other better alternatives which we may not be knowing at this moment. But anyway, so this is how we train the RBM, and hopefully with some level of training, you will be able to reconstruct. Means you can get an RBM which is good at reconstructing whatever input that was given to it. Okay, so now let us check something. Let us check uh, that how on earth do you code this kind of thing. So let us go make our hands dirty now and let us try to code a little bit. Now there are many ways to code such an RBM. For example, there is we can go through PyTorch, or there are simpler options like using the old school NumPy like environment. So what does this code do is that let us look at something very simple. So suppose, let's say you have an RBM, and we what we have decided is that it has NV number of visible layer and in each number of hidden layer. And as this code shows here, this PyTorch code shows, it can have these A and B's, which are just chemical potentials. But main interesting learning mechanic. So here also, as I have shown you, that there is an delta wj etc. is there, how these weights are updated. You can do basically the same things for AIs and BJs, so that's not a big deal. So you can just basically AI get updated just by VI data minus VI reconstruction. Same for BJ, that is HI data minus HI reconstruction. But for our simplistic case, let us get rid of A and B's for the moment because they are simpler ones. And if we know how to code with weights, we can just come back later and update for A and B's. That's not a big deal. So this is a code for RBM, just but we'll go step by step of how to do this reconstruction. So here what we have done is that we have used Python, and for people who doesn't know, what we have done is that we are using NumPy to first code this RBM. Now for people who are not familiar with Python, let us look at few things. Is that there is a class structure in Python, so don't bother so much about it. What we have done basically is that if whenever we code some neural network, etc., we put it in a class. Class is like a type of object that's we're defining. So we're defining my RBM. So this is a class, and this class can have various functions and various structures inside it. And various structures mean kind of hidden layer, visible layers, and all those things. It will contain those information, and it will contain various functions which will act on those hidden layers. So, for example, the first function a class calls is an init function, which is an initialization routine. So as you can see, it is self.nv is equal to nv, and self.nh is equal to nh, self.visible is equal to 1, self.nv, self.hidden is 1, self.nh, and self.random is equal to random random, self.nh comma self.nv. What does it mean? Self.nv means that this class, say, and in Python there is an irritating thing that whenever you are defining a class, this class itself is called self. In some other language like C, etc., you don't have to write self, 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 self many times. But basically, self.nv means this class has a layer called nv, or a layer or just a number called nv, which is the number of visible layers. And the self.visible, this means variable in the class is an array of ones, or it could be zeros also, but I'm initializing that with this an array of ones, and how many ones you have, nv number of ones. So just remember how the restricted Boltzmann machine looks. You have certain visible layers and you have certain hidden layers. You are initializing all visible layers to 1 and all hidden layers to 1. And then what we are doing is that we are defining some weight. So weight stands between these hidden layers and the visible layers. So this connection has certain weight. And so how many weights are there? Weight number of weights is just a matrix. It's in one side it has a number of visible layers, in other side it has a number of hidden layer. And random random means we are creating a matrix of size nh cross nv, and we are randomly initializing this matrix. Good. Then we have some load data, we'll come to that later. But most important or interesting thing is that sorry, what I said is this case is that given a visible layer, this what this code does is tries to generate a hidden layer. Okay, and if we look at it, so first, how does it work? How does it work is given by these activation functions. So I have this is the activation function exponential of WdV by sum of exponential. So WdV is basically self dot omega comma. This is the WdV function. It is basically self dot omega dot v. That function is called WdV. That means that it is, so we are applying first this weight matrix. So how this is done is shown here. This, we are first applying the weight matrix on the visible layer. So you get W into visible layer here. So all this Wij, so for example, what is a visible layer? It's a vector of size nv. So we are first going to a vector of size nh. How you do is to just put the weight matrix on the visible layer, and then you will get a vector of size nh. But that vector itself is not the hidden layer yet. It's just a function from which we'll construct the hidden layer. Okay. So then we have certain activation functions. So basically we have to use this old school activation function 1 by 1 plus e to the power minus x on this function. Good. So I think that I'm lacking a 1 here. Yeah. So it could also be written as e to the power x by sum of, so there is a sum, because what we are doing is that we are basically looking at the, means that these probabilities individually are given by this activation function, and we need to sum over the visible layer part, so to get this answer. So sorry, this sum won't be here, we can do it later actually. So this is the PS. What is a PS is that it is basically a function. It is basically the activation function. For each hidden layer, we calculate this Wij Vj, which we supposed to calculate. So these arrows here means that they are connected by some weight, and for this layer, all this weight means contributing with some W plus something W into V. So this has W into V, plus we have a B, but we are neglecting B and A for a moment. So this is W into B, and then we are doing a Gibbs sampling, means we're sampling with this probability 1 by 1 plus e to the power minus omega I Hj. So how we sample with that probability? We sample with that probability very easily. We define this quantity exponential WdV plus 1 plus exponential of WdV, and what numpy does is that it already does this vector, means that whenever you apply a function, it gets exponential etc, it gets applied to each individual vector, so do not worry about that. Now what happens is that individual components of the vector. Now what we are doing is that we are saying that, good, given this thing, we want to sample a hidden layer. So sampling means just, so how, if I give you a probability, say probability 0 0.4, 0 0.3, 0 0.6, 0.01, how to sample few numbers, say 0 and 1, with this probability? What you do is that you just take some random number between 0 and 1 and see that, or given just one probability p, how you sample a random number with that probability is that you just generate a uniform random number. And what is the probability that this uniform random number will actually be less than this given value p is itself the way to generate the a random variable with that probability. Say we want to generate a random variable so that it is 0 with probability 0.3 and 1 with probability zero point 0.7. So how to do that? What we do is that we just generate a random number which is uniform between 0 and 1, because that's easy to generate. And from that, what we say is that if this random number is less than zero point 0.3, then we will choose 0. And if it is more than zero point 0.7, then we will choose 1. So this new random variable, this chosen 0 and 1, will exactly have probability P of having 0. So we just chose a random variable exactly by this mechanism. And why there is 2 star, etc., etc. From 0 to 1, we have just mapped it to 1 and -1 because we are more interested in spin system. But this part is not essential. You don't have to do that. So you can just do this. You can just basically do this. So that is good enough. But we wanted to map, that gives a 0 1 thing, but from 0 1 we wanted to go to 1 -1. That's why I did it. But it's not essential. Okay. Now what we do is, how now we sample the visible given a hidden. We do exactly the same thing. We take these dots, define these functions. Okay, define these functions, and that is why, that is how we get. And now again, we, if you don't like, we won't map it to 1 -1. I always prefer to do that, but if you don't like, it's fine. 0 1 is fine. Most computer science literature use 0 1, but if you want to go to spin model physics literature, we often prefer 1 -1. Okay, great. So we have both of this function. We now know that given a visible layer, how would you sample a hidden layer? And given a hidden layer, how would you sample the visible layer? Okay, great. And now what is reconstruction of an input? It is just, first we go to the sample hidden layer as by this formula, and then we sample, again resample the visible layer, and that is what is called reconstruction, as we have shown here, that first we sample the hidden layer, then from that again sample the visible layer. So this second layer is the reconstruction of the first layer. Great. Now we know from Hinton's claim that how to train these RBMs, that we need to at the end calculate VIHJ and VIHJ reconstruction. So this is the holy grail of us, and we wanted to calculate them. So now what happens is that there are various ways to calculate them. So I'll show you how to do this calculation. So see, you have in practically how to do this calculation. So you have VH data. Now VH data is that, now this V part of the data is the visible part, is given. It is a given input. Means that you are training on some data generated by some lattice model or whatever it is. So that part is a given input. But H you have constructed. H is not given. What you did is that you have constructed H. So you ask that what is the probability distribution of, means that you have constructed H from this visible distribution. So one, but you do not, now there are two ways to do that. Now here is the thing you should remember, is that you can just look at this VH data, you do a reconstruction and you get all the H's, and then good, I know what is the value of H into Vj just by take outer product, means H all for all H and all V, you look at this common multiplication. Great, that's one way of doing that. But here we didn't do that. A little subtler way of doing that, that each part you keep as probability. Means that when you are calculating this sample, you are hidden, you are calculating sample probability. So why don't you use that probability actually to calculate the expectation, rather than using the whole age to do so, why don't you just use that probability, well, not whole age, sorry, why don't you use that probability, not the resampling of 0 and 1 from that probability. So you can do both. For example, to give you a simple example, means say you have a coin which has a value which you are tossing. The coin has probability of p of getting tail and p or 1 and 1 minus p probability of getting head or 0. Now you ask that if you do it 5 times, what will be the expectation value? You can just take 5 sample, toss of the coin, and you maybe you get 3 ups and 2 downs. So you say that it is 3/5. Next time you calculate it 2/5. You can do that. Means that you can calculate what is called sample mean. Another thing you can do is that you can actually calculate the expectation. You know that it is p into 1 plus 1 minus p into 0, that is p itself is the expectation value. So you may say that, okay, then I'll use p as an expectation. So this is the using the statistical expectation, or another way of going is to just using the sample mean. If you have very large number of sample, the claim is that both of these will give you the same result. But in RBM, etc., you sometimes have a large number of hidden layers, but not always that large. And those subtle differences sometimes create various subtleties in how good this model train, etc. So what we are doing here is that we are keeping each part as an expectation. We are not taking the sample of each in this step, in the VH steps. So what we do is that WDV dot self W dot vis is the weight vector as we have calculated, and then this PS in some ways again. Now they are called H weights. So they are probabilities of turning on those H's. That is the probability. And then you actually use that probability to calculate this VH data. This is also a valid way of doing that, or probability of PS or something. You just use that PS here. You don't do a reconstruction from this PS. So that's a legit way of doing things. Okay, cool. Now, another way to go about it is that uh, means just use you do this reconstruction through this formula, and then you actually use this new HID here. That is the way of going through sample mean. Anyway, so I think it's a little undocumented. Sorry for that, and we should have written here that what it does. But we have two basic important steps: sample hidden and sample visible, and then we have reconstruction, and then we have calculated the first one tt needed for training. And then we have this VH data, and then we have VH reconstruction. Self dot, and then we want to calculate VH reconstruction. So first, why don't you just start with reconstructing the data, reconstructing the input we did, and then we just do the same thing, HOH, etc. We do the same trick. Yeah, so Basically, you don't want to do much here. So once you have done the reconstruction, you can just, what you're doing here is that, okay, good, we have already reconstructed it, and then you just calculate VH data of that reconstruction. That will do, right? So good then. So we know what is VH data. We now have what is reconstruction of VH data. Now we are going for something like a batch gradient. What does this batch gradient thing do? Is that it is nothing, it is just calculating V. So now let me tell a little bit about the data. It is just loading some amount of data. Is just the visible layer is the same size of the visible layer, but there are many vectors like that. So 10,000 vectors, various lattice configurations, or various random tossing of a coin or some with that data or any other kind of data. The same number of input as the visible layer, but many copies of that. So that is the load data part. And what this batch gradient do is that basically looks at all the datas in the set and basically calculate this uh, VH data, and then it is calculating VH reconstruction of that particular thing, and then take the, as Hilton has suggested, this is VH data minus VH reconstruction. That quantity should be used for training. Good. And what update gradient does is that it is just update the gradient depending on the data set and the learning rate. Basically, this part. This is E dot this part. Okay. So that's basically true for all kind of this kind of stochastic gradient descent kind of algorithm. You multiply the gradient by a very small number, then you update the weights. Good. And then update gradient does that, and this learn, this is nothing but just a loop over many thousand of steps, and basically it looks as all the data in these batches, etc., the part of the data, and basically it calculates this batch gradient and update the gradients accordingly. So it just goes through successive updation of the gradient. So this is just a loop over all this update gradient, and hopefully once this we use this learn, something happens, maybe these models learn what is needed, and we'll see that how good do they learn, or do they learn at all. Maybe it won't work. Let us see. So, so this is a very simple way of doing RBM. So what are the complications you can do? Means complication means even in two layers. That is, in this Hinton's formula here, what we have done is that VIHJ data minus VIHJ reconstruction. But how many reconstruction? You can have 5 reconstruction, 10 reconstruction before comparing. Some people do that. That creates some amount of means complication here, or makes these models more involved, or means actually increases the runtime. It's not a big deal here. We have just one reconstruction step. You can have multiple reconstruction. Just write few more copies of the reconstruction or put it in a for loop or something. Great. Now, another thing, as I have said, that this issue of what is probability, what is not probability, that game one can play a little bit and see that what happens at the end, whether you can successfully, in some model, what happens is that we use these formulations, the model doesn't learn very well. But in some model, actually, if you use other formulations, then that learn words. So sometimes this is better, that is better. People have done all kind of complicated stuffs by hub, means you can do various kind of hybrid kind of thing, where it's, some part it use the probability, some way it is given from the sampling. So you can do all those things and make life more complicated. Okay, so now it's time just to see that the code at all runs or it has some error or something. So let us just try. So we define the RBM, that is number of visible layer is 10 and number of hidden layer is 5. The simplest RBM, nothing much is going on here. 10 to 5. And then this is defines an RBM, and learning rate, we are putting some small value 0.001 or something. Okay, good. So now does it learn? We'll see. But before at all learning or anything, just let's see that whether it loads data or not. And data is the simplest possible data. We have just taken some random Gaussian number as data. Or okay. So basically set of random number 0, 1 as data. Some yeah. So this is the data, if just random collection of 0 and 1. Then what we want to do is that we'll see if the things learn, doesn't learn, all those things. But before doing anything, let us just do some kind of fun game. So this data, so let's look at one element of data. It's just a random combination of 0 and 1, just like a perfect coin toss. It's nothing uh, very profound. And what is the size and shape of this data? 10. And how the data looks like, so this is the data looks like. So you can see that this first data 0, just have taken the first sample of the data, and this first second doesn't have any significance here. It's just a random collection of zeros and ones. You could have just taken 3 or 4, whatever you like here, not 0 but 4. You get something. Okay, now this data 4 or whatever it is. Now let us try to do some fun game with RPM. There is this RPM is completely in the virgin state. It hasn't trained yet, so it's completely like it was before. Now, even in that level, let us try to see that if, but you can do some kind of reconstruction. Sample visible. Let's see sample visible. So we want to sample the visible. Sample visible. Sample hidden. So we put this through the sample hidden, and we get some activation pattern in the hidden layer. But why it is minus 1 1? So sample hidden, let me see that why is minus 1 1? 924. Yeah, so now it's proper. So what we have getting is that given a data 4 that is completely arbitrary, but still the RBM is functioning at a basic level. So this is the hidden layer of the RBM now. So where we are in this picture is that we have activated some one and zeros here. Or in my slide, if you go back to that, you can see that there is a pattern of activation of zeros and ones given some one zero etc. We have got that. Okay, now what we are going to do is that, so this is our hidden layer. Now hidden layer, we can see that some activation is there. Now does it also reconstruct after the hidden layer? So sample visible, if we do over that hidden, then what do we get? Yes. So this 0 1, whatever we have given it, has been reconstructed as 1 1 1 0 1, this variable. Maybe I will make some everything float. This kind of things sometimes create problem. So you can see that this reconstruction is not particularly good. So it didn't match at all. But it's expected because it's just a random things, then there is nothing much to learn, etc. But anyway, for whatever reason, let us, if we are interested in teaching the RBM that how to learn something more important, we can do. But first, let us say that this RBM, does it at all learn, or it creates some kind of unprecedented problem? It seems it has learned something. So we are going through various steps. We'll go through 1,000, I think. Let it run. I think it has learned already. Does it improve its reconstruction? Let us check. Possibly not, because it was completely a random thing. So there is not much room to improve, I think. But still, I think it will learn some pattern in it. Yeah. So it is like, yeah. So you can see that it has got some improvement in its reconstruction. So if you take some hidden thing, you actually get something which is even little closely similar to the thing you have taken. So it does reconstruction a little bit faithfully, but here there is nothing much to reconstruct, in a way that it is just like a random thing. The input was actually random. So nothing much to learn here. But can we do better? Is there anything of significance that one can teach the machine? Yes. So one popular thing people always teaching machines is the minced data set. I'll take just 2 3 minutes, 5 minutes more than my time, if that's okay.
That's perfectly fine, Pap.
That's fine.
Yes, that's perfectly fine.
Okay. So what I'm trying to do now is that given that we have a functioning RBM, why don't we put something more interesting to that RBM? So one popular thing is the means data or something like that. But means data may be complicated to some people. So other datas we can generate. Let us generate some kind of fun data. So what can you generate? So let us see. So here, purposefully, I have generated some kind of data which is size 100. So let me reduce the size first. Mm, Sorry. Yeah, purposefully generated some kind of data which seems to have some pattern. Okay, so now what I'm going to do is that, say say we have a data which has this pattern. Now if now we define this same RBM and try to generate this, means whether we want to see that whether this kind of data would actually be learned by this RBM, or how good it can learn, etc., etc. Now here you have, like, we have taken 16 cross 16, there are 256 visible layers, not not anymore like 10 or this thing, but 256. And now we are saying that taking some number of hidden layer is 16. So this is our new RBM. Now what happens if we put this kind of data in that RBM? So does it learn anything? Possibly not, but let us just do that. So we have this data. So data is, yeah, so we have this data, put this data in an array, and what we do is that RBM, we through our RBM we are doing a reconstruction of this data. We get some reconstruction. Now we'll plot that reconstruction. We call it data 2. So You see that you started with something like this, and RBM has completely jumbled it up because it hasn't learned anything. Hasn't learned anything. So to rectify that, let this poor RBM teach some pattern. Teach so whether it has learned to. So this is like a spin configuration: one in some places, zero in some places. So with some kind of learning, whether this poor RBM can actually learn a little bit of these configurations or not. We won't get perfect learning, but I can show you how, in what way these RBMs can learn. So whatever data we have generated, let's just take. So let us do something very dumb, means which one should not be doing, is that we just look at the train data as just this data which we have just given just generated with flatten and all those things, means that we don't keep it in a 2 cross 2 array. And then what we do is that so I'm just taking train data, which is basically several copies of the old data. Yeah, so we got this train data. Now we got means that if we just zero, sorry, so all these data points has a very similar structure. Here is almost the same structure, which is not good for RBM training. You just need to change it. But nevertheless, we just use the same thing as the train data here. So train data is basically copy of this cross shape things. And this copy has been flattened. This is a 2 cross 16 cross 16 array, but we have put it in a 256 array. And what we are doing is that we are training the RBM now with this train data. So how do we do that? Yeah. So RBM first is that load data, train data has been loaded in the RBM. Good. Then RBM goes through a learn phase. So it seems that the RBM has learned a lot. But let us see. We won't complete the learning up to 1000 or something. So this is good enough for us. Let us just see what this RBM has learned, or let it learn up to just say 100. So you can remember that before training, this RBM was giving completely jumbled up output. Now I'll keep it and just do the same. We'll insert the same command here and see how that thing works. So it is still jumbled up. It seems that the, okay, let me see that data, flatten. Mm, Let me see the data RBM reconstruction of the data we are taking, and we'll plotting D2, sorry, data, the shape is that. Okay, so it seems that it's still a little bit jumbled up. I don't know, this RBM seems not to have learned a lot. Let us see. It seems that this RBM hasn't learned a lot here, but it seems that it is slowly getting into some kind of thing. Let me see, 1 second. And yeah, it seems that the RBM needs some. Unfortunately, this RBMs take some time to train. So maybe we don't have that much time here right now. But let us see. Hmm, it's training. Yeah, so maybe this kind of data, I don't know. So this RBM which has been constructed, actually for this kind of thing you need VIs and AIs because it's very position dependent, but I was expecting this RBM will learn something. It seems that this error has gone to zero. That means that it has learned certain things, but as there is no BIs and AIs, it is not producing possibly this very well. Yeah, so it's getting some kind of pattern.
Okay, okay. Sorry, Palab, because
Yeah,
I see that, kind of we're a little bit over time, and I see that already attendees start to leaving us because they probably need to go about their day. You know what I suggest? Would you think that it would be possible that, because also kind of like running programs on the fly is a difficult business. Let be
yeah,
honest with
yeah,
that. Sometimes things go
yeah,
well, sometimes things not go well. And I suggest, would you mind just kind of fixing the program and afterwards sending the Jupyter notebook to me so that I can
yeah,
upload it to the web
yeah.
page? And if
That will
the
be great. So that will
attendees,
actually be great. I'll by tomorrow I'll send you something then with some proper data
okay,
and its reconstruction. This
okay,
the
okay,
thing which I have shown today. Only that.
okay. That would be really perfect, because so that kind of it's sometimes also for students to follow. It's a little bit difficult probably to follow, kind of programming on the fly. For example, you shown
Yeah,
very nice trick how to you take a list and how to make a copies of the list, and kind of
yeah, yeah,
who
yeah,
might
yeah.
not be aware of the tricks like this, and many other examples of like how to deal with the object oriented programming in Python. And I think students will
Yeah,
definitely benefit from the fact that if you can provide us with your code, and I think that
absolutely.
would be really perfect. Mhm.
Okay,
Okay,
okay.
okay,
I'll do that then. I'll do that.
okay. And I will just upload it to the kind of, it will be available from the NITheCS
Okay,
website, where we
okay.
we have all the rest materials available. And do you think that you can also share your presentation slides?
Yeah, that also I'll do. I'll do that. I'll do both.
Okay, that would be great. And if participants have any questions, that's probably the good time to ask questions. But kind of my question is kind of if I can probably ask the question, like you are showing how to write RBM from the scratch, and this is kind of a very nice exercise.
Yeah,
But you also shown how to use, for example, how to use Torch, and what other do you know of other kind of high performance implementation of RBMs? Because like for the simple problems, like for example for MNIST classification and things like this, probably there are many implementations and people could write this own. But if you want, for example, to use RBM as the ansatz for the ground state, I don't know, some relatively large Ising model, suddenly the question of the highly optimized code for GPU or TPU becomes rather relevant. Do you know what are the implementations out
yeah.
there?
So the thing is that so this torch code is not that different from the NumPy code. The thing is that if you write it in torch and then, so for example, there are a lot of this simple RBM without any complications. This which use just the expectation mean as I was describing, etc., with no other thing. So several of these thing is available. For example, in Kaggle or etc. And for example, this unsupervised feature learning, this Stanford tutorial no, activation function, so Stanford tutorial, etc. These kind of places you have various people have put very simple RBMs written in PyTorch. Now, if it is in PyTorch, then the thing is that it anyway runs in GPU. You don't have to do anything for that. So then these PyTorch implementations are generally much faster than NumPy implementation. So if you have a machine by GPU, and best thing to do is to take the simplest of the RBM. For example, you can see a very simple PyTorch RBM. Those kind of RBMs are there in GitHub, etc. Now, I means to recommend means there are many, and the thing is that whatever you are using, the thing is that just see that if it is uh, the basic RBM or they have put anything else with that. That's one important thing to notice. In the sense that in most physics application, we don't want RBMs to be adulterated by any kind of autoencoder or pre-selection, attention or anything. Often computer science applications put various other layers. So one has to be careful about that. That's all.
Okay, okay, okay. And do we have any questions? Okay, it doesn't seem to be the case. So
Yeah.
what I need to do now, I just need, yes, to, okay, so this is
Yeah,
the
you can see
RBM
that
and
there are some
PyTorch.
RBM examples are given, and which is very simple. And
And it's also have use CUDA if there is a if there
yeah,
is NVIDIA drivers, yes, and there is a NVIDIA card, okay,
yeah,
one should
but
use
use
that GPU.
CUDA, it
Okay.
means that it's not necessary in Torch. It uses CUDA by default. But if there is no
hmm
CUDA, I think that this will just run in CPU.
Okay, okay. Okay, great. Thank you. Okay, so I think we can wrap up this mini
Yeah,
school. And as I mentioned before, Palapro sent me his Jupyter notebook and his slides, which I will add to the video lectures of the course, which kind of first three lectures are already available in
okay.
the YouTube channel of the NITheCS, and this lecture will be available later soon, so that everybody could familiarize yourself with with the aspects of the machine learning related to the high energy physics, and this kind of also in partially it's also kind of condensed matter
Yeah,
physics. So, and my job is now just to thank all the speakers. We need to thank all the speakers of this school. Thank you very much.
yeah.
And kind of the next announcement mini schools will be available via the kind of announcement of the NITEX. Thank you very much. Thank
Thank
you.
you.
Thank you. Bye bye.
Bye.